Hello and welcome to week 3. This is topic 1, part 1, and we're going to be talking about convergent plate boundaries and another type of melting of mantle rock we use to create magma, called flux melting. In the beginning here, we can see the product of flux melting, which is the Cascades arc of volcanoes extending from a south sister here in the foreground all the way up to Mount Adams, Mount Rainier way up in the background. Mount Hood, Mount Jefferson, and the rest of the three sisters here, showing a line of volcanoes which parallels the convergent plate boundary, the convergent trench of the Juan de Fuca plate and the Pacific plate. Remember, there are 3 types of plate boundaries: divergent, where we create new ocean crust; convergent, where we destroy old ocean lithosphere; and transform boundaries, or sliding boundaries. Decompression melting occurs at divergent boundaries and at hot spots, where we melt ultramafic mantle rock by raising it, which lowers its pressure and causes melting. And this produces mafic magma, so we get basalt at mid-ocean ridges and oceanic hotspots. Heat-induced melting of felsic crust above the hotspot produces felsic magma, or intermediate magma, through the fractionation, the differentiation of magmas, which creates different minerals which occur at different temperatures and different proportions of melt to crystals. So when we have a higher degree of melting at a higher temperature, we tend to have mafic magmas with olivine, pyroxene, and calcium feldspar. But when we have a lower temperature with a lower degree of melting, that's when we have potassium feldspar, muscovite micas, and quartz minerals, and a felsic magma, like a granite or a rhyolite. Also, to recap, we have 3 types of these convergent plate boundaries. Ocean to continent, which is where Oregon exists. We have an oceanic plate colliding with and subducting underneath the North American plate. We also have an ocean-to-ocean collision zone, where we have ancient, old, and cold oceanic crust subducting underneath younger, hotter, more buoyant oceanic crust. The melting of that subducting oceanic lithosphere goes through flux melting to produce an island arc. And then we have continent-to-continent collision, where we don't have volcanoes, but we do have some melting all the way down just because we're increasing the pressure of these felsic rocks. And we have mountain building, like the Himalayas are the best example of continent-continent collisions probably anywhere in the world. When your subducted oceanic lithosphere reaches around 100 to 150 kilometers depth, seawater gets squeezed out of the rocks of the subducting plate, and this changes the melting temperature of the mantle through a process called flux melting. The water acts as a chemical agent to lower the melting point of the mantle and lower continental lithospheric rocks, which we can see over here on the left. We have our normal geothermal gradient here in this line that I'm following with the laser pointer. Then we have the normal solid boundary here, where we get some minerals starting to melt, and then we have a mixture of liquid and crystals. And then we have the liquidus here, where everything is molten and we have just a liquid. But when we add water, those phase boundaries curve like this and start to intersect the normal geothermal gradient, and the melting curves, they're called, get lowered by the addition of water, and we have melting here at about 100 to 150 kilometers depth within our subducting oceanic lithosphere. This is just another way to show pretty much the same thing at our different situations, where we have a normal crustal gradient where we have the geotherm well away from the solidus, or the line where we get the first melting. A mid-ocean ridge, the geothermal gradient gets really high, and so we have melting at very shallow depths. At a hot spot, we have greatly increased heat at depth, which causes melting at great depth at the base of the lithosphere. And then in an island arc or a subduction zone area, we get the actual solidus, the melting curve, gets changed and goes beneath the geothermal gradient. And this gives us melting at 100 to 150 or so kilometers depth underneath our oceanic or continental lithosphere. To take a step back and talk about oceanic crust for a minute, up here in the upper left, we have basically how the oceanic crust behaves over time. When it first forms, it's really hot, and this encourages the circulation of seawater through that hot crust. You may have heard of black smokers or undersea hydrothermal vents. These are caused by the circulation of ocean seawater through the continental oceanic crust, which makes it all loaded up with minerals, and we get these vents where super mineral-rich water, superheated mineral-rich water, circulates and gets released back into the deep ocean. And this is fed both by shallow magma chambers and just residual heat of that formation of the mafic crust, which lasts for quite a ways. In subduction zones, we have pretty much the opposite thing going on, where the oceanic crust stays cold as it sinks down into the crust. It has a very high heat capacity, and we've already discussed that rocks are pretty poor conductors of heat, and this gives us a low temperature zone as the oceanic crust dives down into the asthenospheric mantle. The plates move faster than heat conduction can restore the original geothermal gradient, resulting in regions of relatively low temperature at very high pressure. This is what happens inside a subduction zone. And we got our two different kinds of melting. We got our decompression melting at our ocean spreading center, and then we have our flux-induced melting here at our subduction zone, where we have the actual wet mantle rock is melting because water has been added to the system, and that changes the shape of the melting curve. This area of low temperature but high pressure gives us metamorphism. That's our third type of rock. We have igneous, sedimentary, and metamorphic, which is a rock that has been changed by heat and pressure and chemical processes. So we get metamorphism at lower temperatures, which normally correlates with a shallower depth than we do at melting, which is in a subduction zone. But we'll discuss metamorphism much later in this course. Metamorphic rocks form overall by solid state alteration of pre-existing rocks due to changes in heat and pressure. In subduction zones, metamorphism creates a very distinctive rock called blue schist, or a blue schist facies, which is distinctively formed in subduction zones. It's this nice, very beautiful blue metamorphic rock. When we look at a cross-section of the subduction zone, we can see this zone of high pressure, low temperature metamorphism. That's our blue schist getting formed right here. But underneath the continent, we still have metamorphism because of the extra heat flow due to the rising magma, and we also have high pressure due to thickening of the continent from that collision zone. So we get other metamorphic rocks like a hornfels, a green schist, an amphibolite, or a granulite. And we'll talk about these much later in the course. You don't need to know these right now. We've already discussed magmatic differentiation to a degree. These are things or processes that change the chemical composition of magma after it forms by melting, but before the magma erupts from a volcano. An example of this is assimilation or fractionation. Assimilation is when your magma melts the surrounding rock, its host rock or wall rock that's called, as it passes through, and adds material of a different composition to that original melt. So you are actually melting your surrounding rocks from your magma body, and this changes the chemistry of the magma because you are melting rocks of a different chemical composition. That's called assimilation. Fractionation is what happens when some of the magma crystallizes as it cools down, which is our forming of mineral crystals, and then the remaining melt is more silica-rich. If it separates out, you make a more silica-rich rock than the original melt by the process of fractionation. We can see it here in this cartoon version here. That's actually Bowen's reaction series, which we already mentioned last week, is the process of crystal fractionation. The first minerals to crystallize at the highest temperatures are something like an olivine. Then you get a pyroxene, an amphibole, biotite mica, different kinds of feldspars, all of which crystallize out of your magma as its temperature decreases and changes over time. Here in this cartoon view, we can see that crystals are forming from our yellow dots, which sometimes incorporates our red dots. But over time, those crystals will settle just from gravity out to the lower part of your magma chamber, which leaves a higher upper body of a magma of a different composition than the original melt. You can see there are much fewer yellow dots in the upper part of the rightmost magma body than there are in the whole, totally liquid magma body seen on the left. And this is exactly the process we see in real magma chambers, where magma goes from being supermafic to being more felsic as different crystals form out as your magma cools down, settling to the base of your magma chamber and leaving an upper body of a different chemistry than the original composition. There are many different processes of magmatic differentiation that produce magmas that are more silica-rich than an original magma body of melt, but not all the time. There's a couple of different ways this can happen, and actually a combination of the two is usually what happens. We can see here on the left that wall rock or crustal rocks are falling into your magma and starting to melt at the same time as crystal fractionation is changing the chemistry of the lower part of your magma. This gives us a widely different composition, not only throughout the individual magma body, but also it affects the whole chemistry of your magma body, which affects what kind of volcanoes and volcanic eruptions you are getting up at the surface. Maybe take a minute to pause this video and look at these two diagrams, and it will give you some clarity on this very complex topic. So to recap, the mantle is very rich in magnesium, calcium, and poor in silica. The partial melting of the mantle by decompression melting creates mafic magmas. Heat-induced melting of the continental crust produces felsic magmas, but partial melting of the mantle by flux melting and magma differentiation creates a wide range of magma compositions, from mafic to felsic, but most of the magma you form in subduction zones by flux melting is going to be intermediate magmas. So we've discussed hot spots producing mafic magmas, hot spots producing felsic magmas, and now we've discussed subduction zones producing intermediate composition magmas. On the mafic end of our rocks, we have an intrusive version which cools underground and crystallizes slowly over a long period of time. That's called gabbro. When gabbro erupts as a volcano, as a volcanic rock, you get basalt. This is called extrusive. In the intermediate spectrum, our extrusive rock is andesite, and our intrusive version is diorite. And on the felsic end, your intrusive rock is granite, and your extrusive rock is called rhyolite. And in addition to these, I will add dacite and granodiorite. These are at the sort of felsic end of the intermediate part of the spectrum. These are your most common rocks that you are forming at subduction zones. It's going to be mostly andesite and dacite. Subduction zone volcanoes, again, can erupt mafic intermediate and or felsic magmas, but most of their eruptions are going to be andesite or dacite. For example, over to Mount Rainier, which is a national park that unfortunately we won't discuss in detail, but the upper portion of Mount Rainier is dominantly made of very fine-grained andesitic lavas. However, beneath Mount Rainier, in the canyons where large amounts of erosion have exposed the roots of previous volcanoes that have existed on the same spot as Mount Rainier, these are volcanoes that no longer exist, that have gone extinct and eroded away, you get coarse-grained intrusive rocks like granodiorite or diorite that formed from the slow cooling of magma chambers that fed long extinct volcanoes. So high up on the volcano, we have fine-grained extrusive rocks like andesite, and underneath the volcano, we have coarse-grained intrusive rocks like granodiorite or diorite. The chemistry of your magma, primarily the silica content in fact, affects your viscosity, which is the runniness, the fluid nature, or is it thick and sticky of your lava, as well as the temperature needed to make a magma. A cooler magma makes for more silica, a hotter magma has less silica. So with viscosity, your basalt, low silica, high temperature, is has a very low viscosity, so it's very thin. Lava flows very runny. These can flow a long distance at relatively great speeds. At the felsic end, your high silica end of your composition spectrum, you have very viscous lavas that are relatively low temperature and generally don't flow very far. These are very thick, very tall lava flows, very sticky lava that makes it not able to flow very far or very quickly. Effusive or non-explosive eruptions at intermediate and felsic volcanoes can come in two forms. One, we have block flows, shown here on the left, where your lava flow is basically a long tongue of large lava blocks. And we have lava domes. In Mount St. Helens' crater, we have a series of lava domes that formed after its main 1980 eruption. And this is a chemical composition called dacite forming this lava dome we can see inside Mount St. Helens' crater. This block flow is made of andesite. You can see it's a little bit more fluid. It flows a little bit further. It doesn't just pile up by the vent and make a big dome. A dome is just a big pile of your lava that is incapable of flowing away from your vent. Let's watch this short video about an andesite lava flow, which is intermediate composition at Santiaguito volcano in Guatemala. We can see that in contrast to the lava flows that we watched in Hawaii, this is not moving very quickly. It's very hard to see it moving at all, and the main part of the flow that is moving is just blocks tumbling off of the front of the lava flow. We do not have rivers of very fluid lava flowing in this lava flow, but this whole mass is moving, albeit very slowly, which we can tell because those large blocks keep breaking off the very front of the flow and tumbling down the slope. This is how an intermediate lava flow behaves. In a previous lecture, I discussed the importance of gases in driving volcanic eruptions. We have a lot of gases dissolved into the liquid magma because it's under pressure, and as that magma ascends, more of that gas will separate out from magma, creating large bubbles. It's just like opening a soda. When you open a soda, you release the pressure, and all of that gas exsolves. It goes from being dissolved in the fluid to being individual bubbles, and those coalesce and rise to the surface, and help drive a volcanic eruption. In lower viscosity or fluid magmas, these bubbles can move faster than the actual melt. They collide and form bigger bubbles, which we call slug and annular flow of lava. This leads to those Hawaiian-style fire fountains, those lava fountains that can be over 1,000 feet tall. We have those two kinds, slug flow, where we have individual really large bubbles separated by, I guess, puddles of liquid magma. And then we have annular flow, where we have a jet of gases, which is driving, bringing along, I suppose, the extra magma along the ridges of your volcanic conduit, which is the actual passageway that liquid magma is rising to the surface within. In higher viscosity magmas, on the other hand, the bubbles move at the same speed of the melt and don't tend to coalesce. So they fragment the magma as these bubbles form and break and burst, which leads to violent eruption of ash, which we can see from Mount St. Helens here on the left. Subduction zone volcanoes tend to have explosive or pyroclastic eruptions. Pyroclastic is our featured vocabulary word for this lecture, and it means, basically when the word is broken down, it means fire or pyro and fragments or clastic. Pyroclastic rocks are fragmented volcanic rocks created by explosive volcanic eruptions. We see a few different kinds here, where our bubbles rise through the magma, and as they reach a certain pressure point, those bubbles will explode, which drives fragmentation of your magma into very small fragments. And we get a very tall ash cloud, which rises through the atmosphere to a point of neutral buoyancy. That's called the umbrella, where it spreads out. And then eventually these ash clouds can collapse, driving something called a pyroclastic flow down the flanks of the volcano. This ash will fall out of suspension in the atmosphere as it cools down, and will rain down onto the landscape below. These explosive eruptions can be in the form of eruption columns with airfall deposits, or pyroclastic flows where these ash clouds collapse and run down the flanks of the volcano, and you also have distinctive block and pumice or ash deposits near the volcano, and in very rare cases an explosive eruption will be a directed or lateral blast, which is what Mount St. Helens did in 1980. So our ash cloud, as I already mentioned, will spread out and drop ash over a wide area. Our pyroclastic flows tend to stay closer to the volcano, but they can still go a long ways from the actual slopes of the volcano. And then our directed blast is driven by a landslide or collapse of the volcano's cone, which we can see here in Mount St. Helens on the left, where we have a landslide gradually revealing buried magma chamber, which then suddenly loses all of its pressure, all of the gas comes out of solution at once, and you get a massive explosion. In Mount St. Helens, this leveled hundreds of square miles of forest and created an actual explosion that was heard for thousands of miles in all directions. Pyroclastic flows are eruptions of volcanic ash, rocks, and gas that are too dense to form an eruption column. These are the most dangerous hazard from any volcanic eruption. We can see here in 1982, this volcanic eruption of El Chichon in Mexico fractured this reinforced concrete wall and bent the rebar in the direction the pyroclastic flow was traveling. This is an incredible amount of energy that destroyed this wall. And this volcanic eruption and its pyroclastic flows killed approximately 2,000 people in 1982. There are linked videos to pyroclastic flows on the D2L page, so please pause this video and watch those. A quick note, they can be frightening, so if you are very sensitive to extreme things, you don't have to watch them, but I do recommend viewing them for seeing the incredible power that these pyroclastic flows can have while they occur. So what kind of deposits do pyroclastic flows make? Well, mostly we have ash, which we already discussed is being composed of tiny fragments of vaporized magma and lava. And then we also have pumice, which is basically a large glassy sponge of frothy lava or magma. The rock we get from pyroclastic eruptions is called tuff, and this is the name for any volcanic rock which is made primarily of volcanic ash. On the left here we have different kinds of tuff. On the top we have an ashfall tuff, which is just made of ash raining down relatively gently onto the landscape. Below that we have chunks of pumice mixed into it, which tells us that this is relatively close to the volcano and could result from a pyroclastic flow. And then down below we have a rock that definitely came from a pyroclastic flow because we have these large angular chunks in it which are called clasts. And they are in suspension, which means they weren't able to settle out down to the bottom of your pyroclastic flow. The pyroclastic flow stopped moving and your large angular blocks were still suspended in your mass of volcanic ash as it was traveling. In the upper right we have one called an accretionary lapilli tuff. Lapilli is a fragment of lava, effectively, that is slightly larger than volcanic ash. So that's just a word you'll need to know, is a lapilli is a large version of ash. And then below that we have a welded tuff, which comes from the largest, most energetic eruptions, where your ash body is so big and thick that it is so hot after it's been deposited by your pyroclastic flow that it actually fuses together and remelts into a solid block, which is called welding. And that's what a welded tuff is made of, from a extremely large, extremely violent volcanic eruption which leaves such a large and thick deposit of volcanic ash and other debris that it refuses together into a solid rock. Tuff is the primary volcanic deposit you get from pyroclastic eruptions. On Mount St. Helens here we have this pumice flow, which is just literally a flow of pumice blocks that was trapped inside a ash cloud. The ash cloud stopped, all the pumice fell out. And then on the left we have two pyroclastic flow deposits. The top one is mostly made of ash, which makes this gray, light-colored tongue coming down out of the volcano. And then we have another pumice flow. These are on the volcano of Montserrat down in the Caribbean. We can learn a lot about how a volcanic eruption progresses over time by looking at the pyroclastic deposits that come out of the volcano. On the left here we have part of the pyroclastic deposits from the eruption of Mount Pinatubo, which is in the Philippines, which erupted in 1990. At the base we can see fall deposits and vegetation. So this is vegetation layer that has ash fall mixed in. So you have your initial large tall eruption cloud, which is dropping ashfall on your surrounding landscape. Then, as that large eruption cloud cools down, it will collapse and form pyroclastic flows. These are called surge deposits, which are your pyroclastic flows. You can see a picture of one from, I don't know where this is, on the right here, going down the flank of the volcano. Very high energy deposits. These are, 70-mile-an-hour clouds of incandescent ash and pumice. And then on top, we have more pyroclastic flow deposits from after your flow stopped moving, so all of your big pieces settle out. So we have very fine ash on the bottom here, which grades upward to larger pieces, which come from after your pyroclastic flow stops, and all of the big pieces stop moving and settle out of your big ash cloud. We get a similar thing here on Mount Vesuvius. This is from a 1940s eruption, where we have fallout deposits, which is the raining ash down. And then as your ash cloud collapses, we get pyroclastic flow deposits about 20 centimeters thick of a fine ash. In the largest, highest energy pyroclastic flows, they will pick up pieces of the underlying surface. Previous lava flows, just pieces of rock of the landscape, and these will be incorporated up inside your pyroclastic flows. So this particular pyroclastic flow includes a chaotic mixture of boulders over 2 meters across to fragments of ash, which are less than 2 millimeters in diameter. So this is a very high energy pyroclastic flow that this outcrop is showing. To recap, basaltic or mafic landforms are usually formed by decompression melting at rift zones and at hotspots. Basaltic lava layers will build up to form a shield volcano, and basaltic cinders or scoria will form a steep-sided cinder cone. Here's a couple of shields here, showing your layers of solidified lava, thin layers, highly overlapping, which make a nice, gently sloped shield volcano seen here in what looks like Iceland in the lower right. Our stratovolcanoes, which are also called composite volcanoes, are what happens at intermediate and felsic volcanic centers. We have a tall, steep-sided volcanic cone, which incorporates both lava flows and pyroclastic rocks, which pile up to form a big, steep-sided cone. These are much steeper than a shield volcano, but less steep than a cinder cone, which is just made of loose material. As we look at this cutaway of a theoretical composite volcano, we have a bunch of different parts to it. In B, we have the magma conduit, which extends upward through the center of the volcano, to the vent, which is at G, which feeds the crater at the summit. And extending outward, radiating from the summit of the volcano, are lava flows and pyroclastic deposits that have built up the volcano over long periods of geologic time. Also, to recap, calderas are collapse features. The smallest ones are mafic or basalt, the largest ones are felsic. Crater Lake, which is a caldera and a subduction zone volcano, is intermediate in composition. Crater Lake formed when a volcano called Mount Mazama had a particularly large and cataclysmic eruption that caused the mountain to collapse downward into the magma chamber, which was emptied by the size and violence of the volcanic eruption. After the mountain summit subsided and collapsed down into the magma chamber, that left behind this big caldera, which has since filled with water and created a beautiful lake. So now let's talk about Crater Lake National Park, one of our great national parks, the only one in Oregon. Its big eruption that led to the collapse of the volcano occurred 7,627 years ago, plus or minus 150 years. It started as a moderate-sized rhyolitic pyroclastic eruption on the northeast slope of Mount Mazama. Geologists call it Mount Mazama. The Klamath-Muckaluk people of the region call it Giwas. Enough magma erupted from this volcanic eruption that the weight of the mountain caused it to sink downward and collapse into the magma chamber through ring fractures that formed around the perimeter of the volcano. We call these ring fractures and ring dikes once magma intrudes into those fractures and begins to erupt. The mountain summit sank further and further into the magma chamber, which left behind a caldera that later on filled with water, over 1,900 feet of water in the case of Crater Lake. Over thousands of years after the main eruption, lava flows and a cinder cone volcano formed in the bottom of the caldera. One of these, Wizard Island, now stands up as an island in the middle of Crater Lake. The lake filling the caldera is now 1,949 feet deep, the second deepest lake in North America and the deepest lake in the United States. So I've overlaid Crater Lake over Portland's aerial imagery, and we can see that Wizard Island, the island that stands up in the middle of Crater Lake as a cinder cone, is about the size of downtown Portland, and that's just the island in the lake. The actual size of the caldera, which is over 6 miles across, extends from the summit of the West Hills all the way to Interstate 205, all the way in East Portland. And from north to south, it goes from Lombard Street all the way down past Powell Boulevard, almost to the city of Milwaukee. So it's really, really big. When you go to Crater Lake, you'll see that it's a lot bigger than you think it is, and it's really, really impressive to look at from the rim and down toward the lake surface. Something really cool that we get from these particularly large volcanic eruptions like Mount St. Helens, which excavated the top 1,200 feet of the mountain, and Crater Lake, which removed the top 5,000 feet of the mountain, gives us a chance to look at the interiors of stratovolcanoes, or composite volcanoes. Mount St. Helens used to have a nice, triangular, beautiful, symmetrical cone. After its eruption, we can see what the inside of the volcano looks like because it had a massive landslide which removed that top 1,200 feet. Mount Mazama, on the other hand, gives us a look at the entire circumference of the volcano. Mount Mazama was probably about 12,000 feet tall, just based on looking at the slopes of the mountain and where they would have converged above the present Crater Lake. The caldera, as I already said, is about 5 miles across, so we have a 5-mile wide circular cross-section of the inside of Mount Mazama, which gives us a look at the life and times of a large stratovolcano. We can see the strata, the lava flows that have built up Mount Mazama, dipping away from the center of the volcano, as we can see here on the right in this cartoon version. They are tilting away from the old summit of the volcano. So we now get what looks like horizontal layering on the caldera wall, but that is really because these lava flows are tilting away from us and we are looking at them end on. So they look horizontal, but they are in fact tilting away from the center of the volcano. Here's a larger, higher resolution image where you can see these horizontal lava flows. Most of these are andesite lava flows, or basaltic andesite. They look horizontal, but remember they are tilting away out from the volcano. Also in this picture we can see the oldest rocks of Mount Mazama, the 400,000-year-old phantom ship. Most of the rocks we see in the rim of the caldera range from 400,000 years old to the youngest ones, which are about 8,000 years old. But we can see that it is made of hundreds of overlapping layers of lava flows. We can also see parts of the ancient plumbing system which once fed eruptions on Mount Mazama. These are called dikes, which are cooled, vertically oriented igneous intrusions, and they are the cooled remnants of the volcano's plumbing system. We can see this planar intrusion of basalt standing up prominently above the surrounding caldera because it's A, vertically oriented, and B, much harder than the surrounding lava flows. This would have fed an eruption that came out of the flanks of Mount Mazama and fed a lava flow that cascaded down the slopes of the mountain. One of the youngest rocks we see at Crater Lake is a large lava dome called Lau Rock, which is a tall cliff, some of the tallest cliffs around the perimeter of Crater Lake. It's about 7,800 years old, so it erupted just a few hundred years before Mount Mazama's cataclysmic eruption, which created Crater Lake. It began as a large explosion crater which blasted out a crater on the slopes of Mount Mazama. That crater was then filled in with lava, which made a lava dome. This rhyolite was unable to flow very far from its vent, so it just piled up, filled up that crater, and made a lava dome. After the cataclysmic eruption, half of that lava dome collapsed downward and filled in the caldera, and the other half of the lava dome now stands as a prominence above the rim of Crater Lake. There's a few of these remnants of lava domes that are large solid masses sitting atop or filling holes within the layers of those surrounding lava flows. We can see the base of that lava dome right here on this line that I'm tracing with the laser pointer above those otherwise outwardly dipping, horizontally appearing layers of lava flows. And that is the end of part 1 of lecture 1 for week 3.